We have a definite integral from 0 to 2 of x cubed times the square root of 4x squared minus x to the fourth dx. This is different than the other ones that we've looked at because the ones we've looked at involve something like a squared minus u squared in a square root, or the square root of a squared plus u squared, or a plus bu. Here we have a variable showing up in both terms inside of a radical. For that, we actually go to the very end of the table, and we have forms involving the square root of 2au minus u squared. And if you were to look through the integral tables, you would see by process of elimination that this is going to be our best bet. For this, we note a couple of things. Our radicand should be 2au minus u squared. From that, I surmise that a is equal to 2 and x squared is equal to u. If x squared is equal to u, then I know that du is 2x dx. Therefore, I'm going to split up the x cubed into an x squared and an x. And so this becomes the integral from 0 to 2 of x squared times the square root of 4x squared minus x to the fourth times x dx. Because our du is a 2x dx, I know that I should multiply and divide by 2. So I can see my du, and then I can see that I have 2 times 2u, so that reinforces that a is equal to 2. And u squared is x to the fourth. I can write that down just to make it really explicit. U squared is equal to x to the fourth. So we can actually rewrite this integral without even knowing what form we're going to be using. I'll deal with the limits in just a minute, but the integral is x squared times the square root of 4x squared minus x to the fourth. The x squared out front is u. The 4x squared minus x to the fourth is in the square root is going to be the square root of 2u minus u squared. I missed an a. I peeked over here. It's 2au minus u squared inside of the radical. So we have 2 times 2u minus u squared du. We then know that we're looking for a form that looks like u times the square root of 2au minus u squared du. And I see that right over here. Before we get too ahead of ourselves here, though, we do have limits that we need to change. Because x goes from 0 to 2 and u is equal to x squared, u must go from 0 to 4. Now let's see if we can see. Wow, that's a long form there. Oh my goodness. All right, I put a box around it so we don't lose it, but I think we only need a portion of it. We don't need to know what the integral looks like on the left. We've already identified what we need to from that. And we also don't need the plus c. First of all, we would know to put it. But second, this is a definite integral, and so we aren't going to be using a constant of integration anyway. So I'm going to zoom in so I have that much on the screen. And I'll just start writing this down. This is 1/2 times 2u squared. Now, we already decided that a is 2. So when we see minus au, we're going to say 2u squared minus 2u minus, now 3a squared is going to be 12. That whole thing over 6 times the square root of, lost it, 2au is going to be 4u, and then minus u squared, plus, now we're here at a cubed over 2 times the inverse cosine. So we've got 2 cubed over 2 times the inverse cosine of 2 minus u divided by 2. Now, that whole thing has the 1/2 out front. Let me graduate the parenthesis to a square bracket. Actually, the second square bracket, I'm going to just say we're evaluating from 0 to 4. We're done with the integral table now. And at this point, we're going to substitute 4 in place of u everywhere we see it, and then a 0 in place of u everywhere we see it, and subtract. So we've got 1/2. Well, you know what? Look. 1/2 distributes to the denominator of 6. But we also have it. No, that's how I'm going to do it. 1/2 distributes into the numerator, right? So 1/2 times 2u squared minus 2u minus 12 becomes u squared minus u minus 6. And then way over here in this term, we have a 1/2 on the outside, a 2 denominator here, and then 2 cubed in the numerator. That 1/2 is going to divide into that, leaving 1 factor of 2. Now, evaluating 4 in place of u, we're going to get 16 minus 4 minus 6, all divided by 6, times the square root of 16 minus 16, well, that whole term's gone, plus 2 times the inverse cosine of 2 minus 4 over 2. That's going to be negative 1. All that minus what happens when we put 0 in place of u. The whole first term, we have u squared, nope, it's the square root. 4 times 0 minus 0 squared, that's a factor of the first term, and so we get nothing from that one. And from the second term, we have 2 times the inverse cosine of 2 minus 0 over 2, so the inverse cosine of 1. Put it in parentheses so it looks better. So the first term went to 0. Let me underscore this because that's what happened when we put 0 in place of u. And 2 times the inverse cosine of negative 1. Well, the inverse cosine of negative 1, the angle whose cosine is negative 1, is pi. And the angle whose cosine is 1 is 0. And so our answer is 2 pi. I know that got a little messy at the end there. But I encourage you, if you got lost at all there, go through and do all the steps on your own, and then double check the work that you see on the screen, and hopefully you'll see where everything landed. A point I would like to make at this point is that now we know these integral tables exist. If throughout the rest of the textbook you come across an integral that just looks terrible, it may be that the author intended you to look at one of these forms in the integral tables. You see, as he goes through the rest of the book, he assumes that you've seen these. And so every once in a while, there's one that would be best served by looking at one of these tables.